Welcome to Inorganic Chemistry. In this lecture, we'll introduce molecular orbital theory and look at simple homonuclear diatomic molecules. Okay, let's look at another simple diatomic or homonuclear diatomic. They have the same two atoms, dioxygen here. So using our principles of LCAO that we just discussed, we're only going to use the valence atomic orbitals on each oxygen. So that's the 2s and then 2p, right? 1, 2, 3, okay, on each oxygen atom. I didn't draw these in the correct energy scale. But then we need to decide, so those are the valence atomic orbitals, how are we going to combine them? We need to consider their symmetry. And we can get the symmetry of orbitals by looking at the character table for that point group. So what is the point group of dioxygen? Well, dioxygen is a linear molecule which has a horizontal mirror plane. So this is a D infinity H point group. Look at the character table for D infinity H. We see all the irreducible representations here and two different symbology for those representations. To find the symmetry, let's see, we know the s orbital on the oxygen atom is the most symmetric, right? It's a sphere. So the most symmetric irreducible representation is right here. So the s orbital is going to transform of the oxygen in the D infinity H point group is going to transform as A1G or sigma G plus. It should be a sigma G. Okay, so sigma G plus. Now, what about the p orbitals? Well, we can assign them x, y, z axes. So in the point group, here we go. Usually we're going to assign the bond as the z-axis. That's also the primary rotation axis, so that works out well. So then let's make this x and this y. So we have p orbitals along these three directions. So they have these p orbitals have the same symmetry as the axes, which if we go in this area of the character table, we see the z-axis is going to transform as sigma u plus. So that's sigma u plus ungaradas u. Okay, and then the px and the py are going to transform as the x and y, and you see that they're transformed together. X comma y in parentheses transformed together as pi u, a twofold irreducible representation. So we know which atomic orbitals to use and which ones are going to interact with each other. We're going to put this together to make a molecular orbital energy level diagram. And the way this works is this axis is the energy increasing as we go up the page. So let me draw this more to scale. The 2p atomic orbitals are higher in energy than the 2s. Now our symmetries, sigma G plus on the 2s. So we're going to have the atomic orbital energy levels for each atom that are going to combine on the sides of our diagram. And then in the middle, we'll create the MO, the molecular orbitals. And we know the 2s sigma G plus can only interact with the other 2s sigma G plus on the other oxygen atom. So they'll combine a linear combination to make a bonding molecular orbital and an antibonding molecular orbital. We know that just like with our dihydrogen. Let's look at the p orbitals. We have sigma u plus and we have the pi u for the two types of symmetries for the p orbitals. So the sigma u plus are going to combine together to make one bonding molecular orbital and one antibonding molecular orbital. Okay, and the pi u transforms together. That means if we start with two atomic orbitals here, we need to make 4 molecular orbitals. 2 would be bonding and 2 antibonding. so now we have all of our molecular orbitals. We started with 4 plus 4, 8 molecular or 8 atomic orbitals, so we should have 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. So that worked. We need to figure out what to call these molecular orbitals. We know this is a bonding molecular orbital from the sigma atomic orbital. So we're going to call the molecular orbital lowercase of the atomic orbital. So this is a sigma from the S, and then this is a sigma also from the S, and it's antibonding, so we'll put a little asterisk or star there. This is a sigma from the P. This is the sigma from the P antibonding. This is pi, I guess you call it XY. And this is pi antibonding from the XY P orbitals. Okay, so now you see where sigma and pi bonding comes from. Finally, we need to figure out where are the electrons. We've figured out the energy levels, and I should point out why these p orbitals are degenerate. They start out the same energy. They have different symmetry, but they have the same energy. So why did I put the sigma bond lower in energy than the pi bond, and also the pi antibond lower energy? The sigma overlap is a stronger overlap than the pi overlap. When you draw your orbitals in class, you'll see sigma bonding, head-on bonding of those two p orbitals, is going to be more overlap, and so that's going to be a stronger bond. But in the same sense, if you can make a stronger bond, then you make a stronger antibond, or more antibonding, or higher energy. Same way that pi is less bonding, so the pi star is less antibonding. So that's how we got that relative order here of our molecular orbitals. Now in your handout you're going to do difluorine, and you're going to get a slightly different result than this because of hybridization, which we'll get to in our next part of our lecture. But before we do that, let's take into account what happened to the electrons. So these are the orbitals, and by convention we kind of think of the electrons as filling the orbitals, even though we know from quantum mechanics the orbital is the electron. But anyway, let's look at our valence electrons on our oxygen. We have 1, 2, 3, 4, 5, 6 valence electrons in our oxygen atom, and that's going to be true for both oxygen atoms. Now we're going to combine them and fill our molecular orbitals, just like we're going to follow the same rules: Pauli exclusion principle, Hund's rules, Aufbau principle, for filling these molecular orbitals with our 6 plus 6, 12 valence electrons. Okay, let's start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So my molecular orbital energy level diagram is now complete. I have the relative energies of the orbitals, I have the symmetry labels of the orbitals, and I have filled in the electrons for the orbitals. And notice how I have 2 unpaired electrons, just as experiment shows that dioxygen is paramagnetic. Before we get done with dioxygen, let's look at another concept, and that is the bond order. We can compare our molecular orbital theory result for explaining the bonding in a molecule to what we've already know from the Lewis bond theory. The formula for determining bond order is to take the number of electrons in bonding molecular orbitals, subtract from that the number of electrons in antibonding molecular orbitals, and then divide by 2 in order to pair them up, like for Lewis bond pairs. For example, let's look again. Here's the Lewis structure for dioxygen. This tells us that we should have an oxygen-oxygen double bond, or a bond order of 2 is what we should expect. Now we know this Lewis structure isn't accurate because it doesn't show any unpaired electrons. Let's go back to the dioxygen molecular orbital energy level diagram and count electrons. So we have 1, 2 in a bonding molecular orbital here. These are antibonding. 3, 4 bonding. 5, 6, 7, 8 bonding. Okay. 8 bonding electrons. Minus, these are antibonding. 1, 2. These are antibonding. 3, 4. 4 antibonding electrons. Divide by 2 equals, well, 8 minus 4 is 4, divided by 2 is 2. So a bond order of 2 is what we get from our molecular orbital energy level diagram for dioxygen, and that corresponds with the model, Lewis model, for the bonding in dioxygen. So MO theory should give the same type of result as Lewis bond theory, but it adds to our understanding of the bonding by helping to explain why we would have two unpaired electrons in the molecule. Okay, we're going to take a break and we'll come back and do a heteronuclear diatomic molecule.